All right, welcome back. This microphone is way too loud. I'll put it down there. So we are getting to the end here. How's the proxy coming along? Going okay, hopefully? Yeah, it's a real project. I mean, you're really building something that could be used in the world for as a proxy. So I think in that sense it's a good assignment. But it does have some challenges to it that I'm sure you're finding as you're going through it. The final assignment will be out at the end of this week, and then due at the last day of class, which is like the Friday after Thanksgiving. So you've got a fair amount of time to do that as well. Today we are going to go back to what we talked about on the first couple of days of class. And in fact, Phil has been better than me at actually bringing these things up as we go along in the course. But the first day, we started looking at principles of system design. Okay, and let me see if I can make this bigger. I cannot. I will go through the principles of system design as we do this. But I wanted to step back and talk a little bit about the big picture. So there are 2 more lectures. They're going to be on non-blocking I/O and maybe something else on, did you say caching maybe? I'm going to talk about a little bit about caching today. And then that will be that. But we talked about these big ideas. We did a lot of implementations in lecture. You saw a lot of code, and there was lots of example code, and of course you wrote a lot of code for your assignments. But the big idea is we wanted you to walk away with an understanding of a few basic principles that guide design and implementation of some of these larger types of projects. Okay, larger types of systems. You talked about file systems, multi-threaded RSS feeds. Like that's a pretty big thing going on where it seems like, oh, it's just pulling from a bunch of servers, but it's pulling from all these different servers around wherever they happen to be on the internet, and that tends to be a big thing. The proxy is another one that's a reasonably sized project, and then of course the last project is that Phil's already talked about is MapReduce, and that's another one that is really used in production at places like Google and other companies that have taken on, that have decided to use MapReduce type ideas. And so we want to give you kind of the basic big picture of some of these things. Where can you go from this class if you want to dig a little deeper? If you happen to be a CS major and you haven't yet chosen a particular concentration, systems is one of the choices, and there are a whole bunch of other systems types classes that you can take. I would say the first biggest follow-on, there it goes. The first follow-on course that really kind of directly follows this course is CS 140, Operating Systems. Whereas in this class, we use a lot of the things like multi-threading and multi-processes and file systems, and so although you did build kind of a file system layer. 140 is just as much about writing those types of things. Like they will give you as an assignment, here's a very bare bones thread system for a particular operating system, and you have to make it better, and you have to make it more robust, and you have to actually go deeper into the code and write the threading library. That's the kind of thing that CS 140 goes into. And of course you learn a lot about the big ideas of what operating system design is all about, and why operating systems do things the way they do, and what does it mean to have a computer where you can have multiple people logging in at the same time, or you can have a server that has thousands of connections coming in. The operating system has to handle all that, and whereas we talk about some of the hey, here's some of the things operating systems can do, you go down and learn about why they can do that. So 140 is a good class to follow on if this stuff interests you and you really do want to know a little bit more about the details. CS 143, compiler construction. Compilers is a class that if you want to know how you go from a C or C++ program to the assembly language, like how does that actually work? How do you walk through those layers? Compilers is a great class to take. I think compilers is one of my favorite classes in graduate school. I loved it. It really gave me a different perspective on programming languages and programming language parsing, and how you end up going and using, taking the language description and being able to go through and parse a program and turn it into binary. Yeah, Michaela?
Just a quick question. Do you know who's teaching CS 143 this spring?
I don't know who's teaching 143 this spring.
Not on Explore courses, and it was a different person last year.
Yeah, I'm not sure who it is, to tell you the truth. Hopefully it'll be up pretty soon. If you email me, I can try to track it down. I'm sure we know this at this point. Somebody knows anyway. Or maybe it's just random. I don't know. Who knows? Phil, you're not teaching 143 in the spring, you know. Okay. 107E. Oh yeah, so well, 107E, that would have been a pre-course. I'll have a couple comments on 107E going forward as well. Just on some of the things some of the abstractions that you might have seen there as well. So 144 is computer networking. Phil has taught that course before, certainly. 144? We've taught that a number of times. Yeah, it's networking. If this networking stuff interests you and you do want to go a lot deeper into the concepts about how networking actually works, we're going to talk about a few different of the networking layers. We're going to talk about kind of the big picture of networking layers, and the networking class goes into those details, and you write a lot more code related to that. And I think it's a very good follow-on course to this as well. In 110, what do we emphasize? We emphasize like using sockets and API functions and so forth. And CS 144 is all about, again, implementing some of those other layers. So it goes definitely deeper and into the, hey, how do you implement some of these things? And I'm sure Phil could answer lots of other questions about 144 as we go. All right, so those are some of the follow-on types of courses you can take if you enjoyed this course. And for some of you, this may be your last course in systems as well, and you might be like, I'm done, or we're all done. But that's that. Okay, so on the first day, we talked about these principles of system design. There are 7 of them that we thought were important here. Abstraction, modularity, layering, naming, caching, virtualization, concurrency, and client-server request and response. And on the first day of class, some of these you might have thought about these, but not really known where they are. I hope you know something about concurrency at this point, because we spend a lot of time doing that. And of course, client-server request and response, that's kind of what you're doing now with your proxy assignment, and it will also be some things you have to think about for MapReduce, and it's also in RSS feeds and so forth. And so let's go through some of the things here. I've got some new examples for similar things that describe some of these that hopefully you'll find interesting, and then we'll tie it back into the things that we've kind of talked about this quarter. Okay? All right, abstraction. So the big idea of abstraction is what? It's separating, in our case for programming, like the behavior from the implementation. And we talk about this in lots of different ways. If you have a sort function, and in fact, we've used the sort function in C++ frequently, has anybody ever dug in to see what algorithm the sort function does? Maybe, maybe not. If you have, it's actually, believe it or not, I think it's a combination of either, depending on which system you're using, either merge sort or quick sort with an insertion sort for very short elements. So basically, it does a broad pass of like quick sort or merge sort generally, and then when it gets down to arrays that are like 10 elements or fewer, just does an insertion sort, because that's actually quicker or just as quick in general than a full-blown quick sort. So anyway, the point though is that the abstraction is you have all used the sort function many times, but the behavior, and so you know the actual behavior of it, you know that it sorts your elements, but you haven't necessarily gone and looked at the implementation because it's not pertinent to what you're doing. Does it work right? Does it work fast enough? Yes, that's what you care about. The behavior you care about. You don't care about how they implemented it. Okay, and sorting is interesting too. People are still doing research on different types of sorts. Who's heard of shell sort before? Anybody ever heard of shell sort? It's kind of like it's a general, slightly more generalized version of insertion sort, and we still don't know the asymptotic complexity of shell sort, and it's been around for decades and so forth. So there's people are still doing research on that sort of thing. Okay, so what else about abstraction do we care about? We care about defining a clean interface. So we've written a lot of interfaces for you for this class, right? We've given you some libraries that have decent interfaces, and we've given you, for the most part, a lot of the, hey, here's how we want the interface for your programs to run. Why do we do that for our class, and why do we do it in a lot of these types of classes? Well, first of all, we want you all to be kind of going towards a certain, we want to point you in the right direction, let's put it that way. It would also be a little hard to grade some of these if we didn't have the ability to say, hey, do it kind of using this framework. But that's making a clean interface is certainly an important part of abstraction. Because again, you don't really care what the implementation is, but you need to have that barrier between the behavior and the interface so that you know how to use, or between the behavior and the behavior and the interface, so that you know how to use the interface and it's actually a clean enough interface. Some would argue that there are a lot of things in C++ that are not particularly clean. When you look at do a find on a map and it gives you a first and a second pair, and you have to think about all that, and it's most people end up just doing auto because they can't figure out that it's an iterator pair and whatever, and not necessarily the cleanest thing in the world, but there for a reason, and there certainly because some people thought it was a good idea and a good thing there. What sort of things, this is what we put in the first day, examples of abstractions we have taken for granted or that you would still take for granted this quarter. File systems. So you looked at the file system at a very low level as far as, once you get the data off the blocks and so forth, but we generally abstract that up. We didn't do too much of that in this class with the file star abstraction, but that's a C language abstraction, which says, look, we don't have to worry about writing these while loops around read or around write, so that we know how many bytes are sent and all that. Let some library do that. That's certainly an abstraction. The I/O streams that we've used in the most of the class, including the sock stream, I/O sock stream, and so forth. Those are just abstractions that abstract away the details, so you don't have to worry about it. You don't have to worry about the buffering. You can actually use the double angle brackets to output and read and so forth. So it's a nice abstraction in that sense. But we did learn about some of the lower level things like file descriptors and how do we actually use that abstraction for a bunch of different layers, which we'll talk about pretty soon. Okay? What else? Processes, right? You, at this point, have used fork many times in this class, and you know how it works, and basically what it does and so forth. You might not understand how they work under the hood. Like you say fork, and all of a sudden now there's two processes, and they're exact duplicate and so forth. And we've gone into some of those details. But that's another abstraction where you say, oh, I'm going to fork, and now I've got two processes that are identical. And the details of how that happens. Yes, it's nice to know that there's virtual memory there, and that you only do copies when you need to, and so forth. And those are things that, as a programmer, you'd understand. But there's an abstraction layer there as well. Signals. Signals is another abstraction, right? You know that signals are used to tell the kernel, hey, something just happened, or I want to tell another process about that something happened, and I want to send a signal to that other process. You don't necessarily know how that's implemented under the hood. Okay, there are other classes where you can learn about that sort of thing. So there's an abstraction. You know the behavior, you don't necessarily know the implementation. Threads, same sort of thing. You can create C++ threads. You know how to join them. You know how to, you know that they have shared memory and so forth. You don't know how they're implemented yet. Take CS140 if you care about that. Another abstraction, HTTP. Right? HTTP is a protocol, and you have used it when you have done things like get and post, and you're doing that for this assignment. And you have used that abstraction, but again, you care that your data goes to some other server. You don't necessarily care how it gets there. Take the networking class, and you'll learn a lot about that. Okay? So that's abstraction, kind of in the big picture, and some of the ways we've talked about that. Let's talk about modularity and layering. We've talked about layering a whole bunch in this class, particularly when it came to file systems. We started off right away, and we said, here's a whole bunch of layers to file systems. Okay, what is modularity and layering? Subdividing a larger system into a collection of smaller subsystems, right? You've done this since CS106A, where you've decomposed your problems or your programs, right? You write a helper function, you are basically taking something and making it a little more modular. Okay, why do you do that? Because you might call that function from many places in your code, so you don't want to duplicate it. You might also care that, oh, if I know that this function is working and I call it from another function, I don't need to worry about debugging that part. I can kind of know that part is, I can debug it much easier. And that's one of the reasons we decompose. But making it into a smaller subsystem is important. One of my favorite examples of a kind of thing that's super complex that really benefits from modularity and smaller subsystems. We've all used like photocopiers before, right? We've all used photocopiers and whatever. In Gates, we have some of these like giant photocopiers that are great for like making hundreds and hundreds of exams for CS 106A and 106B and whatever. Although we use Blue Book now in most cases, so we don't have to do quite as much of that. But a copy machine, think about how complex a copy machine is. Like, what does it have to do, right? Well, it has to make a copy, of course, right? It has to take the paper and it has to actually like somehow figure out how to copy it. So there's got to be some lenses in there and lights and so forth. It turns out there's lasers. These things have lasers in them, right? To if you send a document, it actually to draw it on the screen. It also has to do the reverse. Like, how do you get copier to do both sides of the paper? Well, either you have something that can somehow draw on both sides and put toner on both sides of the paper, but that's almost never what happens. It really flips the paper over. That becomes a mechanical engineering problem, right? Does anyone know how copiers actually work, like how they do their thing, right? It's kind of cool. The laser or an electric wire actually charges up the paper where the dots need to go, and then it charges a bunch of that horrible black toner in the opposite charge, and then it dumps the toner on the paper, and then it shakes it around, and then it dumps off the excess toner that doesn't stick to the places that are charged, and then it fuses it with a big heater kind of thing. It fuses the toner on there, and then what else does a copier have to do? And that's how the copier actually works, and it's kind of cool. What else does a copier have to do? It has to staple, right? It actually has to have a stapler in there that feeds the paper in there, and it has to collate things, and it has to do that. And why am I telling you all this about? Mainly because I think they're kind of cool, but I think they are really a giant. It's a system that no one person at Xerox or anything could describe every single part in any level of detail of a particular photocopier, because it has so many different parts and so many different modules to it, and everybody has to, and they have mechanical engineers, electrical engineers, computer scientists, and lots and lots of subsystems in that. And big projects are like that, right? Your phone is another great example, right? If you took CS 107E, we talk about all the different sensors on your phone. Okay, anybody know how many sensors are on your phone, roughly, in your phone? 25, that's probably a pretty good guess, right? There's probably 25 different sensors in here. If you bring the phone up to your face, ever notice that like the screen goes a little dim, right? Part of that is because there's an accelerometer in there. Part of it is because there's a little sensor that's a little camera on the front that, not the main camera, but another camera that tells that it's near your head, right? There's the touch screen, of course. There's the button. There's all the feedback that you get. There's radios in here. You know there's 4 different radios in your phone? 4 different radios. There's one for the regular cell phone, which nobody uses anymore. People don't actually talk on the phone anymore. There's the Wi-Fi radio. That's a radio. Bluetooth's a different radio. There's the Apple Pay, if you've got that or whatever. There's a little radio in there that broadcasts to. Actually, it may be just a sensor that amplifies the signal. But there's many different things in here. This is a huge system that needs to have modularity. Again, you can go to Apple and ask anybody there, hey, how's the iPhone work? They will all give you 1,000 different answers about what their little particular piece is, but they probably don't have any idea about some of the other things on the phone. In fact, many of them. So you need to make this modular if you're going to make if you're going to make a system that has any complexity to it. Okay, you're probably not going to end up knowing everything about whatever project you work at your company, wherever you end up working, right? You'll know a very small part of it, and hopefully you'll know you're contributing to something bigger. But that's what you need to think about when you're subdividing things, because it has to be that way. Otherwise, we'd never be able to figure it out or make things work. Okay, file systems use layering. We've talked about layering a lot with the file systems, right? We've got the symbolic link layer, and we did a lab where we talked about the symbolic links and how symbolic links need to be turned into or actual files themselves, which have a path, and how you actually go and get the absolute path, which is another layer. You've got the path name layer. You've got the file name layer. The naming layers are for the humans, basically. right? I mean, part of it is for the system to be able to be, in a form that's in order, that's ordered in some way. But part of it, most of it, is for humans. Like the computers wouldn't necessarily care about the names. It's the humans that care about the names of these things. You've got the inode number, right? You've got all these file names, and then you've got this inode, which is a number, which is much easier for the computer to actually utilize, and it distinctly points to an actual file, and the inode number actually says, hey, this is the file itself, even though it may have many paths that lead to it, and so forth. You've got the actual file layer, which is about the bytes coming on the that are in the device, and you did a whole bunch of work on trying to figure out, how do I break this file into all these blocks for the actual bytes, which is another layer. The block layer, of course, is the layer that the disk itself has blocks on it, and you did a whole assignment on that. Okay, so there's lots of layering that we've talked about in this class as well, okay, particularly with file systems. What else? G++ has a bunch of modularity to it. I'm actually going to show you a little example of how G++ breaks your program that you're trying to compile into a whole bunch of steps before it gets to the last step. Okay, there's the preprocessor, which is if you do pound includes, which we do all the time, and then sometimes we do these pound defines as well. I'm going to show you a little example of this. But there's a whole bunch of layers. Let me just show you a program that, let's see, we'll go here and we'll go, let's just call this hello110.cc. Okay, and let's do a little program, and it's going to be a C++ program. Include IO stream, okay, using namespace std, okay, pound define k range start, and we'll say it's 100, that's how you do a pound define, int main, int argc, char star argv, and then we've got that, and then let's do a little for loop. For int I equals 0, let's start it at k range start. I is less than k range start plus 10, I plus plus. Let's do that. And then we'll just see out hello CS110. Okay. And then we'll do I, and then we'll do an endl. Okay, like that. And then return 0, and there's your program. Okay, that's a pretty simple program. Okay, let's see what happens when we compile it. Anybody see any bugs in the program? No, hope not. G++, or actually let's do Clang++, because on my computer I can do, there's a different compiler that has a little more details that are shown to the user. So we'll do Clang++ hello110.cc-o hello110. Oops. Okay, hang on, move hello11 to hello110. There we go. Hello110 should do, there we go. Okay, did everybody expect that out of the program? Hopefully you expected that based on the little simple for loop, and it just counts down and what have you. Okay, let's actually compile this using just the preprocessor. Okay, if I do Clang, turns out you have to do Clang in this case, -e, and then we'll do hello110.cc. Okay, did you see all that fly by? Well, that's the output from the preprocessor. Most of this is, remember with the preprocessor, it takes those pound includes and pound defines and processes those. With the pound include, it literally finds the file you're including and just pastes it into the code. Okay, that's what pound include does. Pound define actually changes the code itself. If you look right here at the bottom here, look what it did. The pound define that we had was k range start, and it was 100. This is after the preprocessor. Look what came out. It says int I equals 100. It just went and replaced k range start with 100. In fact, it replaced it over here too. It was 100 plus 10, and it just replaced it there. Okay, that's one level of modularity that the G++ or Clang does for you. Yes, Christian.
I'm curious if that's the case. Why do we have to sometimes in the .h file and the .cc file, we have to include the same thing? Why? They just have to replace
Yeah, good question. So the question is, hey, what if you include a header file in the C++ file and in the other header file, or the C++ file and the header file? The preprocessor is smart enough generally to ignore the duplicates. So it says, oh, I've seen that one already, and then it doesn't redo it like that. In some cases, if you do that with variables and things, you need to have some more preprocessor directives to say, hey, don't include this twice, or don't look at this twice. But most of the time, it doesn't do that. Okay, so that's what the preprocessor does, and it does all this stuff that most of it is just pages including the other files in there. Okay, if we look at this and then do through WC, word count, 41,000 lines for that little Hello World program, right? And it's kind of amazing that G++ works as fast as it does sometimes because it has to do, and 41 kilobytes is not a lot in the big picture, but that's what the preprocessor does. Okay, after the preprocessor works in G++ or Clang, you go and you do a lexer phase. Okay, a lexer phase says, oh, every one of the characters in your program means something, right? Now, if it's in a string, like only really the beginning and the end of the string are important. Everything in the middle is just other parts. But all the different keywords and variable names and all that actually mean something. So if you do a lexer, we can do that. We can show what the output of the lexer is. We have to do it this way: clang-xclang-dump tokens, and then hello110.cc. It actually puts output both to standard out and to standard error, as it turns out. I'm not sure why it exactly does that, but when it does it, it does it. So I'm going to just pipe standard error to standard out. Phil has showed this in class before. And then I'm going to show you what comes out of this. All right, well, remember it has to preprocess. This is some of the preprocessor stuff. It tells you, oh, I found a word called typedef. Oh, and we're going to call it a typedef. They're pretty good about naming in general, but it's found that word. That word is an atomic part of the program. Typedef is an atomic part of your program. Okay, let me do this. I want to show you hello110.cc. Let me just comment out couple of these things, and in fact we don't even need the C out. I just want to show you a couple other things about this. If we do it again, okay, so this is actually the without any of the other details. In fact, if we do it through word count, if we do it without the preprocessor there, it's only 38 lines of output. So that's a little bit nicer because we don't have that much to do. But here's what the preprocessor is doing with our program, right? Well, it says, oh, I found an int. Right? And it says I found main, and I found up left parenthesis, right? Well, how do you know what all these things are? Well, your program starts out and it's int main, like this, parentheses. Well, it takes that and it figures out, oh, there's the first interesting part of the program, int. And it says, oh, that means it's an int. The return value, as it turns out. And then it finds main, and that's an important. But then it finds the left parentheses, and it actually calls it L_parenthesis, etc. Okay, so you have all those in there. It finds the comma. I mean, how often do you think, oh, that comma is important to me in the program? Well, it is important. If you left out a comma, right, it would end up like breaking your program, right? Well, the lexer knows about the structure of a C++ program, and it needs to actually pick out all the different pieces. So they're all in here. Let's see, what else do we have? We've got identifiers, and we've got the less than is in there, and we've got the plus. We had a plus in there. The plus came out, and there's part of it, right? This is what the lexer is doing. It's another layer of the actual processing of the compiler. Okay. What do you do after you lex it? Well, then you parse it. So the lexer, so far, what we've done is all rote. Like you can actually just go and, okay, look, I'm looking for, what do I get? Oh, I have MAIN. Oh, that's inside, I know that's an identifier because it comes in this part. It's pretty rote, the lexer part. The parser has to know the syntax of C++, and it has to work on, in a little bit more detail. Let me show you how we can compile a program to show the output of the parser. clang-xclang, let's see, -ast dump and then hello 110.cc. Okay, this is the AST. It stands for the Abstract Syntax Tree. The parser is now taking your code and turning it into. It didn't compile because it has the. I didn't have the pound included in there still, but it takes this and it actually knows how the functions are, or how the actual C++ language works, and it finds all the different parts for this. So for instance, let's go down here. There's a compound statement. In that function I showed you, there's a for statement. Well, that for statement, it says, oh, there's a for statement as part of the tree here. And the for statement has, as part of it, it has a declarative statement. Then it has a binary operator in there, which happens to be the less than, because I said the less than part in the for loop. It's got the, it actually has the literal number 100 that's part of the tree. And what's it going to do? It's going to compare that to the 10 that we started out with, or it's going to add it to the 10. Actually, there's the add. So it's got plus in there, and it's going to add the 100 and the 10 together. And then it's got the plus plus in there, and so forth. And this is now going to the semantic level of your program. Okay, whole nother layer in here. Okay. After you do the parser, then you get into this one, which is the semantic analyzer, which goes and confirms that you've got a program that's actually going to work. Now, it can break on any stage of this, right? If you if you have something that breaks on the lexer phase, you'll get an error there. If it breaks on the parser phase, you'll get an error there. And the semantic analyzer then says, are the types correct? Are you using the correct type here? Did you cast things correctly if you needed to, and so forth? And this is all getting it ready so that it can output the binary. Unfortunately, I couldn't figure out how to make Clang give you the semantic analysis output, but that's that. And then finally, you get the code generator stage, okay? And the code generator stage, you basically need to do, let's see, I think it's just, actually, let's go back and make it hello 110.cc. We'll put back in the important parts here. And we'll do clang ++-s hello 110.cc. And that actually produces hello 110.s, which is your assembly code. Okay? The cool thing about Clang as a compiler is it actually tries to comment its own assembly code. Kind of nice. Didn't get that out of G++ too often. Some of the interesting things about the assembly code, and that's basically the final step before it translates the assembly code into binary, and that's a very rote translation as well. That's the final level. Interesting thing about this, let's go up here. You can see the cout function here. All right, this is the whole cout function here, and you'll notice it doesn't just say cout. If you had looked at a C program that was compiled into the assembly and it kept the labels like this, it would just have cout. For C++, you can't do that. You can't actually have just cout because C++ allows overloading of functions. You could have 10 different couts that all take different parameters. So what C++ has to do is what's called name mangling. Kind of a cool name, but it does name mangling and turns your cout into this like ___ ZNST3 business so that you can correctly identify it in your program because it might be overloaded for some other cout. But anyway, that's the layering that can go, and the modularity in that sense that can go into a compiler for your code. There's all sorts of different parts to it, and you can then pick and choose the parts. One of the nice things about Clang, again, is that you can build, the way they built it is you can build your own lexer or your own parser and then just kind of connect it into the rest of Clang and get the benefits of part of the program while creating your own modular part of the other one too. So it's a neat system in that sense. Okay. All right, so that was compiling, layering there. Okay, what else do we have? Computer networks. Okay, computer networks, of course we have lots of layers for networks. We've seen a bunch of this already in as we've done networks. Okay, we have two protocols that we've generally talked about, TCP and IP, which at least TCP we've kind of talked a little bit about. TCP talks about how the data should be packaged and transmitted. Okay, and it actually goes into more details than we've talked about. TCP is the part of the network that says, oh, I'm going to break your your data into packets, which are smaller parts, and it's going to put like a number on that packet, and then it's going to shoot it off to the other server, and it's going to eventually, hopefully, get to wherever you're trying to send it. And the other end, the TCP layer says, "Oh, I've got a packet. What number was it? What happens if two packets come in out of order? Why would a packet come in out of order? Maybe they took two different routes along the internet, and it just happened that you get packets out of order." TCP handles that. Okay. You also have another one called UDP, which is a different type of one that doesn't care about how consistent the data is. It doesn't actually care that all your packets make it. UDP is used for things like video streaming. Has anyone ever done Skype or Zoom or whatever, FaceTime, and it gets a little blurry, and you can still hear hopefully, but it gets a little blurry and whatever? That's because your network connection is not that great, and it's sending it along a path that if some of those packets drop, who cares, right? I mean, you care because it's blurry, but it's not bad enough that it has to like retransmit them so you get a perfect picture. You can have things dropped. Okay. There's lots of layers. We didn't really go into all these layers, but there are layers in a network. I'm sure you talk about these in network in 144. There's the application layer. This is the layer for your program, and your program generally doesn't care about how the data gets from your computer to some other computer you're trying to make the request at. You just care that it gets there, and you might care that it's there correctly, like you would use TCP and so forth. But you don't care about the actual underlying process at the application layer. We just hope that it works, right? If you do go down to the next layer, you've got this layer called the transport layer. This is where the TCP part lives. This is the part that breaks your data into packets and sends them correctly and says, I'm going to count them and make sure they're all there and send acknowledgments when I get it, when I receive a packet, and send resend a packet if I don't get an acknowledgement of the packet being sent. All those details that you can learn in CS 144. That's what the transport layer does. You've got the network layer. Okay, the network layer is the part that delivers the packets end to end. Okay, in these are the ones that you have like a to address and a from address, and it doesn't necessarily care that the packet gets to where it's going perfectly. TCP will take care of that. It just says, hey, send this to the next hop. Go to the next place along the various hops of your network. And then finally, below that, you have the link layer, which is, let's say, Ethernet or Wi-Fi. Those are two different ways. If you plug in your computer, you're connected to Ethernet. That's a completely different way of sending the data in the physical sense than doing it through the radio in your computer over Wi-Fi. And the network layer delivers this data to the link layer that actually makes it go from your computer to the next hop directly, like the router in the ceiling or the router in the wall that you've got things plugged into. So there's lots of layers for networking. And of course, you'll learn more about that in CS 144 if you take that. We learned more about the application layer things. We did dig into sockets and so forth. We didn't really talk about bind too much, but those are some of the layers for the networking. And you hopefully you got a little bit of a picture of some of the layers in there. Okay, what else do we have? We've talked about naming and name resolution. We've seen that with files. Of course, humans, as I've said 1,000 times, humans prefer file names and path names because it works better for our brains to understand things in those numbers. Computers are probably better with inodes and block numbers, right? Because they're numbers. And you spent a lot of time in assignment 2 managing how to discover inode numbers and deal with the file blocks and all that. Based on a file name, right? You had to go search for it through the path of the various directory entries and so forth. Okay, humans. That wasn't me, was it? It was. Hold on. Fell right off. Humans also care about domain names. Phil talked about this, and when you go and you look up google.com, the computer turns that into an IP address. How? Through this DNS server that says, oh, I'm going to look up how do I get to google.com and how do I find the various IP bytes attached to that name. Okay. Phil also talked about what was it? Let me see if I can find it on here. Phil did this trace route call, right? And he showed trace route. In fact, it was weird. I did some of the same trace routes you did in class, and on my Wi-Fi in my office they work fine. If the Wi-Fi here they don't work. So it's a little bit bizarre that sometimes the trace route, maybe it's the router that happens to start the process. But if you go to, let's see, this one I happen to go to I did a trace route to a place in Australia. I went and said, I want to know what the different hops are to get to this place in Australia. And there's a whole bunch of ones in here, right, that are interesting. You've got a whole bunch inside Stanford, SUNet are the ones inside Stanford. Then you go to this one called CNIC. This is one that Phil showed you the other day. This CNIC happens to be a computer, it's a consortium of universities in California that have all decided to connect their networks together. That's what CNIC happens to be. Then it goes to, remember we're trying to get to Australia, it goes to this one called PacificWave.net. And I had to look up what PacificWave.net was, and PacificWave, yes?
Seattle, Washington. STTLW.
Yeah, so there you go, Seattle, Washington. And in this case, it happens to go to someplace in Seattle, Washington. And I looked up PacificWave, and it's a company that actually sends data to other nations like underwater, like literally in cables underwater. And let's see if I have this on here. There it is. You can go and look up a submarine cable map of all the different cables that are underwater. And if I want to go to Australia, there's a whole bunch of underwater sea cables. This one, look at there, there's Seattle up there. This is probably the one that it actually connects on there. And then this one looks like it goes to Japan, and then maybe there's one down here. I guess Seattle's up here, so maybe this one goes to Hawaii and then goes down to Australia there. Submarine cables are interesting. You might think, wait, why are we doing anything with underwater cables when we've got cool things like satellites now? But there's various reasons. Satellites are super expensive to run. Many communication satellites happen to be in what we call geostationary or geosynchronous orbit, which means that you send them off and they are far enough away that they orbit the Earth in one day, meaning they stay basically above where they are 24/7. That makes it nice because you can point your dish at one place. It's always going to be right about there. Anyone know how far away geostationary orbit happens to be? All you people in the Stanford space, whatever, no? How about 22,000 miles away, right? That's kind of far away. That's far enough away that it takes about 1/8 of a second for light to get to that satellite, and then another 1/8 of a second for the light to get back, like on a different place on the planet, okay? Which means that you've got about a 1/4 second delay in anything you do. And has anybody ever called people overseas and gotten a connection where you like say something and then it's a little bit of a delay and it's a hard conversation? When I was on a ship in the Navy, I would call my mom from the ship, and it was a satellite thing, and she hated it because you'd talk and then like a second later you'd hear, and she'd be like, I hate it, I can't talk to it. Just call me when you get to Singapore or whatever. And then I would call from Singapore and it would actually be fine, and I go, I wonder what the difference is, and it's because it probably used some undersea cable, which is much shorter distance. The question that always comes up is how do they actually lay these 3,000 mile long cables? They have a big ship with a big spool of cable on it and a bunch of spools, and they just drive the ship along the water and they unspool these cables. When it gets to the end, they bring another spool on and somebody splices them together, the ends, and then they drop the layer and they put they make it so it's hopefully waterproof and in fact shark proof. That's another big one. Sharks actually they have these like sensors in their noses that can tell about electrical signals, and so they will go and like look at these cables and sometimes take bites out of them and whatever. So they try to avoid they make the cables thick enough and whatever. But this is one of the links that your data might go through, some underwater system. And then let's see, for Australia, it ends up going along PacificWave, and then it gets to Australia. And then it goes to a whole bunch of hops in Australia before it actually gets to, this was the University of New South Wales, and a whole bunch of hops there before it gets into the computer on that other end. Okay, so you can see traceroute, and that's, this is, where did it go? There we go. This is the kind of naming and name resolution, and this is the resolution of an IP address trying to get to a different computer via the internet through a whole bunch of hops. Do you have any other comments on that? Yeah, Phil did the whole part of a lecture on that. Okay, so we spent some time learning on that. What are the things? URLs. URLs are generally human readable. Process IDs are not necessarily human readable, but they're numbers that describe a process that we can use in our programs. All of these things are various names that we have or numbers that we have for a particular thing on our computer. Okay? Yeah. Yep.
I think one of the ones in MapReduce, like the buckets, right? And hashing.
Hashing is another, yeah, and the buckets for MapReduce, like how do you know which computer to actually send the data to be mapped? It's based on a hash, and that's another example. Okay, questions on that? So what else do we have? Caching. So we haven't talked too much about caching in here in this class. I think, Phil, you said you might want to talk about it next week a little bit. So we may get into a little bit more detail about that. But what is a cache? You're using a cache in your proxy function, right? What's the purpose of a cache? To speed things up, right? How does a cache speed things up? Well, it basically takes your data and puts that data somewhere that's faster to access than it would be in the original place where it was stored. Okay, how does that manifest itself on? How does that manifest itself in the? Let's say in. Let me go over here. There we go. How does it manifest itself in your computer? Well, your computer has a hard drive or an SSD or something like that, right? This is where data is stored that is in a form so that you can turn your computer off, get on a plane, turn your computer off at the other end of where you are, and it's still there, right? You've also got memory, like main memory, and by the way, this is like many gigabytes of memory, like hundreds of gigabytes or a terabyte of data or whatever. You've also got main memory, which we've mentioned a whole bunch of times in this class, which is memory that's volatile, and it's on your computer. When you turn your computer off, it actually goes away. So if you're going to like close your computer to sleep, it actually saves that to the hard drive, so it can put the computer to sleep. But in main memory, this is normally like 8 gigabytes or 16 gigabytes or something like that. And it's a fair amount of memory. Turns out there's other memory systems in your computer. In CS 107, you talked about, or 107E, you talked about registers, right? And between here, except in CS 107E, there are a whole bunch of caches that are other forms of memory that, like, you've got an L1 cache, an L2 cache. You might even have an L3 cache. It's the other way around. Sorry, it's the other way around. L1 is lower, L2 and L3 is up here. And this might be, L3 might be 256 megabytes of data or something. That might not be kilobytes. I don't even know how big it is. 2 megabytes? Yeah. Let's say 2 megabytes of data, but significantly less than your main memory. But it's going to be faster than your main memory. What makes it faster? Well, often it's built directly onto the processor itself, so that when you're actually requesting it, you don't need to go over some bus to get the main memory. Phil's going to look up some of these details maybe, and you don't have to do that. But it's on the thing. L2 is another one that might be like, I don't know, 256. This one might be 256 kilobytes or something like that. The details aren't quite important. But it's another layer of even faster memory, but smaller amount. And then you've got an L1 cache, which might be even smaller, and it's going to be even faster. What makes these faster? It's the way they build them on the chip. Why don't you make all of your memory L3 cache, for instance? Or sorry, L1 cache if it's faster than L3? Because of space. Maybe it takes up more space to make the to make a faster cache or something like that. So it's all these trade-offs. And then of course you've got the registers at the bottom. So let's talk about different speeds for them of some of these things. The whole point is if you request memory from your hard drive, it goes into main memory, like maybe a buffer or something like that that Phil has talked about a number of times. If you use it, it also can go into L3 cache if you're going to use it more often, let's say, or L2 cache or L1 cache, or finally onto registers. And there's various ways that you decide what information to keep in these caches. But the more often you're going to use something, generally, the longer it's going to stay in these faster parts of memory so that you can access them a lot faster. Let me give you a little example, and the numbers are not going to quite be exact. But if you have a register, let's say we're modeling a register out of the following. I have a pen, and I need to pick up the pen and write something down. okay? That might take, like that's like the amount of time to do that. If the pen is sitting on this table right here, and I pick it up and I write something down, that's modeling like register behavior, how long it took me to do that. If I go to my L1 cache might be, hey, the pen is over on the other side of the room, and in order for me to go get that pen, I need to walk over there, come back, and write down the data. That's going to take a little bit more time, right? L2 cache is like, oh, the data might be over in Gates, and I have to walk over to Gates, pick up the pen, come back here and do this. L3 cache is like, oh, maybe the data is down in downtown Palo Alto or something like that, right? It just takes longer and longer. Main memory is, oh, let's say the data is up in San Francisco and I have to walk to San Francisco, pick up the pen, and come back. Wouldn't you much rather have the data you use frequently be somewhere down in the cache, right? Somewhere lower that it's much faster to actually access. Okay, this is why we have caches. SSDs and hard drives, that's like, oh, your data's in New York City, and I need to like walk to New York City, pick it up, and come back. That's how long it takes to get your data there. So the minute you get data from the hard drive, you instantly put it into main memory, because the odds are good that you're going to want it again, and it's much, much faster, like millions of times faster. Yep.
In the context of this example, what would getting data from a server be?
Yeah, getting data from the server is like the moon, right? Not quite the moon, but it's definitely more. It's more like, oh, I have to walk to New York City, then I have to get on a boat and sail to England, and then I have to, and then I have to take, a bicycle down to Africa and pick it up. You know what I mean? It's so much slower in that sense, right? Which is again why, look, the cloud is great, but trust me, you also want local files too. Right? Because you don't want to have to do that. So again, those numbers are all more or less made up, but that's the scale of what we're talking about for these sorts of things. Okay? So that's what caching does for you. Okay? And caches are a very important part about making your computer fast enough to run your programs the way you want that. Okay? Another example of caches is like your web browser. You have seen you're going to use that right now. Why do we care about that? Same sort of reason. If we have multiple people using our proxy and we know there's a site that has the ability to be cached, it was a GET request that can be cached, then we might as well store it because the next request will be much faster to get. Okay. What I want to show you now, I just want to take a few minutes and show a hardware cache, how it might be implemented. Okay, I'm just going to take a few minutes on this. Anybody take EE1? I think it's 180. Do you do caches in that 108? No? Oh, all right. Well, there are some classes where you might do this, but I'm going to show you an example of how you might have memory and a cache, and how you might decide whether or not to update that cache and how you might do that. So let me do this. Let's see, I want to do this. I want to make a blank screen here. There we go. Let's say you had 32 bytes of memory. Okay, 32 bytes of memory. And how many bits do you need to represent 32 bytes of memory? Anybody know? 2 to the what is 32? 5, right? You need 5, so you'd have like 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, dot, 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 all the way down to 1, 1, 1, 1, 1, and you get your, whoops, 1, 1, 1, too many ones. You get your 32 bytes of information, okay? These are like addresses, let's say, all right, for your memory. And let's say you have that. Now, if we have a cache, and a cache is generally a smaller amount of memory, okay? Let's say we have a cache that can only hold 8 bytes of memory. How many, and I'll do it like this. How many bits do we need to hold 8 bytes of memory? 8, 2 to the what is 8? 3, right? So you need 3 bits to represent the 8 bytes of memory. This we'll call the ID, okay? The identifier in this case. Okay, so we would have, let's see, 8 different bytes. 1, 2, 3, 4, 5, let's see if I can get this, 6, and then one more, 7, 8. There we go. Okay, it's going to be a little bit small. But it's going to be like 0, 0, 0, and then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. And there's our data in our cache in this case. Okay, they're the identifiers. We're also going to have a couple of other pieces of information here. We're going to have what's called a tag, and a tag is going to be 2 bits wide. We'll see how that goes. Then we're going to have some data that we keep in the cache as well. Okay? Let's say that we want to use this cache to store data from our 32-byte data store. And we're going to store the following data. Okay, I'll write them all down here. 10110, 11010, 10110. What'd you do in 110 today? I listened to Chris list off a bunch of binary numbers. Hang on, let me. What's that? We've got 110 in there. There you go. Let's see. Let's do a few more anyway. 11010, 10000, 0000011, 10000, 10010. Two more. 100. Let's see. That was a 0. 100. No, sorry. That should be a 10. And then 10000, and then one more. 11010. Okay. We're going to look up those memory addresses. Okay. What you do, okay, is you say, oh, okay, I am going to take the memory that I want to get from my system. And I am going to look at the bottom, as it turns out for this system, the bottom 3 bits. Okay? And that makes up our ID. Okay? And you go into your cache and you look at 110. And you go, does 110 have anything in the cache yet? And the answer is no. Okay? So this is what we call a cold cache. In other words, you can have a cache that's cold or a cache that's hot. A cache that's cold doesn't have any data in it yet. In fact, and Phil, correct me if I'm wrong on this, if you happen to know, when you change processes on a thing, the caches mostly go away, don't they?
We used to.
They don't anymore? Okay, this is I've got old data. Now they have tagged cache. So, but you can have a cold cache and a hard. In this case, there's no data in the cache yet. So what this means is, we need to go to main memory to look up our 10110. So we go over to main memory. This takes a while. And we look up that data. And then we say, oh, good, now we've got the data. Let's store it in our cache. Well, how are we going to do that? We're going to go to 110. Okay, we're going to go to 110, and we're going to store the rest of the address, 10. In other words, the tag part of this address. Okay, because there's only 8 addresses here, from your 32 bytes, 0 will go to 0, 1 will go to 1, 2 will go to, or 1 will go to 1, 1, etc. Where do you think address 8, in other words, 1000, goes to? It goes back up to here. It's a modular thing, right? It just says, oh, look, I'm going to put that one there. So in this case, we keep the tag. So what do we have now? Now we've got this. And by the way, in the data here, we put the memory at location 10110. Okay? All right, let's do another one just to see. This is now in the cache. We've got fast memory that holds our data for 10110. Okay? All right, let's look at the next one here. 11010. Well, what do? We go to 010 up here, and we look at nothing there. It's cold again. So what we do is we put the 11 for our tag here, and we go grab the data from memory address at 11010. Okay, we have now had what we call 2 misses in the cache. 2 cache misses. You can either have a miss or a hit. A hit is where the data exists in the cache and it's much faster to get. Okay, let's look at the next one. 10110. Oh, we've seen this one before, right? Great. Let's look up 110. We'll go to 110. We look at the tag and we go, is it the tag that we would be using for this data? 10110 is. Now we grab the data from here, and that's called a cache hit. And we don't need to do anything else. We never need to go touch main memory. So we actually have a win in this case. We have a cache hit, and it takes there. Let's do a couple more here. Let's look at 11010. Well, we've already done that. That's also in the cache. Same thing as before. So that's another hit. I'll just put hit here for that one. Okay, 10000. Well, we don't have anything there. We would do 10, and then we put the memory from 11000 in there. And that, 10000 there. Let's look at this one. Let's look at one that we've already, let's see, 011. We don't have that one. 000. Yeah, let's look at this one. No, let's say this was 11000. What would we do? We would go here and we'd go, okay, let's go to 000. Oh, there is something here. Good, so far so good. Is the tag correct? Is it 11000 that we cared about? No, it's 10. Oh, too bad. We have another miss. We need to now go to the cache and get the data from 11000 and then update the memory here. So you can do that. So do you see how this basically works? You have data in your 32 bytes of main memory. You only have 8 places to put that data. So you have some scheme based on the address to actually take the data and put it into your cache. Okay? This is called a direct mapped cache. And there are other kinds of caches called associative caches, which basically allow the data to kind of find a separate spot in the cache. Okay, and there's other things about that. But what's the benefit of this? You get to use main memory. What are the downsides? Well, sometimes you have, if you are trying to look at 2 bytes of memory that happen to be 8 bytes apart in your main memory, you're never going to get a hit because you'll look at it, put it in the cache, and then look at the next one, which would be in the same place in the cache, and then it'll be a miss, and that's not so good. Most of the time, caches don't just grab 1 byte of information at a time. They grab a whole bunch of nearby data so that you know that you can, the odds are very good that you will look at that nearby data as well. Question?
Why are ID and tags separate? Could you possibly implement it using a hash function?
Why are ID and this basically is a hash function in some sense, if you think about it. I mean, it's hashing the ID. You only have 8 spots. So we might as well use the last 3 bits of our address because those are going to be the 8 spots that you'd want. But yeah, you could do it in some other way. This happens to be fast. That's another thing. You can very easily mask off the bits of an address, and it's super fast in that case. Instead of trying to run through some other hashing algorithm or whatever, that would be slow. Remember, the whole thing is about speed in this case. That's part of it. Yeah, Phil?
I mean, so one of the problems is if you do that algorithm, you choose the last 3 bits, then it can be that there are 2 things that have the same last 3 bits, and you're trying to use both of them, and they start ping-ponging in the cache. They keep on flushing each other, and so you often have more complex caches where you're set associativity, but people still do things like trying to lay things out exactly in memories that would get good cachealization. And then I think it was in 2012, Intel said, all you people are messing up, we're now just going to hash addresses. And so basically,
So they do
just
that.
get spread evenly across the cache. And so your peak performance is lower because you can't control things, but your average case is higher and you can't screw it up.
Yeah, there's a whole branch of research on when to remove things from a cache and when to leave things in a cache, and so forth. There's entire conferences dedicated to like this sort of thinking about that. And people at Intel and at other big chip companies have to think about this stuff to make their computers fast, to make your processor fast. Yeah. Okay. So that was a very quick intro to caching, just to kind of see how that works on your computer itself. Let's go back to our thing here. As I said, you're using a web cache for your thing. Your browser. Some of you have already found this problem. In fact, one of you put a little link on Piazza on how to turn off your browser's cache for this assignment if you want, so you don't have to actually keep having to clear it. But why does your browser keep a cache? Same reason. The odds are you're going to go to the same page multiple times, and if you keep clicking on CNN.com, well, there's some parts of that are going to be exactly the same from one time to the other. There's a whole bunch of images, like the CNN logo. They don't change that very often, right? So that can be kept in your cache, and that request you don't need to re-ask for that data, and so it speeds up your browsing history. Okay. DNS caches are also the same sort of thing. Trust me, your computer already knows what Google's IP address is, for instance, or at least the network, the router does, right? Because people are Googling things all the time, so they keep it in this cache. Okay, questions on caching? All right. All right, what else? Virtualization. So we've talked about virtualization a number of times. In fact, Phil did a great lecture on RAID, which is the multiple disks that have your data either duplicated or more commonly both duplicated and using an algorithm that keeps it so that it can do error correcting, and so that you can get you don't lose data if one of your hard drives dies. You don't lose the data because it's copied onto other parts of the disk or a hash of it is, and so forth. So you can recover that. But that's virtualization. That means for your computer, your computer thinks there's one hard drive, at least the files, the Unix, let's say, thinks there's one hard drive, and this RAID system that you set up says, oh, I'm going to take the request from the operating system, and I know how to get that data off these disks. Okay, it's virtualized and abstract. It's an abstraction. It's another form of abstraction, and it's abstracted away from you. Okay, so it makes many resources look like one. Okay, the AFS system, where you log into Myth, right? All of you have accounts on Myth or on the AFS system. We all do at Stanford, and that AFS account, the actual data can live on various hard drives in various places on various computers and so forth. And but as far as you're concerned, there's one file system. In fact, AFS is actually worldwide. Like if you have the right permissions, you can go to Carnegie Mellon and browse their drives straight from your Myth machine without logging into Carnegie Mellon, because it's all on one big shared hard drive, or rather shared file system. Okay, so there's issues there. Web load balancers are another one. If you are a company that has lots and lots of people requesting your web data, you want to spread the load for all those requests across lots and lots of machines. Okay, so a web balancer or a web server load balancer would do that for you. And so you can have a small set of machines to intercept all the requests and just farm them out to the various machines. Okay, when you log on to Myth, that's what happens. You know how you log into Myth and you actually go to Myth 67 or you go to Myth 53, right? That's because there's a load balancer there that says how many people are using Myth 55. Oh, too many people, I'm going to send you along to Myth 54 or something like that. So that's that. Virtualization can also be making one resource look like many. Okay, so you can virtualize that. The virtual addresses, we've talked about a whole bunch of time in this class, where you have every process thinks it has access to the entire memory system, and then there's a translation layer that says, no, really, there's only 16 gigabytes of memory, and your process gets this chunk, or your process has these addresses that are physical addresses, yet you think they are somewhere else. That's just virtualization. Okay? Threads are a virtualization system where a process's stack segment, although you do have multiple stacks, or you have each has its kind of own stack segment, and multiple threads can kind of utilize that. Okay, and that's making many or one resource kind of look like many, right? The stack in that case. Virtual machines. How many people here have used like VMware before? VMware, I think I've got VMware on here. Yeah, VMware. With VMware, what you can do is it allows you to, let's see, I've got a couple different computers on here. I can open up my VM and I can run a completely different operating system on my, within my own operating system. And once this opens up, I'll be running Linux. And as far as the operating system is concerned, it thinks it's running on real hardware. Now, I think they built in ways for you to actually ways for it to actually know that it's in a VM. But sometimes you can build a VM that doesn't even know it's in a VM, right? That's virtualization in that case. Some people say that we live in a virtual machine, basically, that our universe is a simulation that was built from some other universe and all the way up, and there's only one at the top, and some people say it's actually very likely that that's the case. But virtualization in this case is the way we can make one computer have multiple different types of operating systems running at the exact same time, completely independently as well. Okay, let's see, and let's see what else. There's VMs for the Java runtime. Whenever you run a Java program, there's like a virtual machine that's running that program and doing the translation into actual binary code for your program. Okay, that's virtualization. We've seen a whole bunch of examples of that in our class. Concurrency. I hope at this point you know a little bit about concurrency because we've seen it a lot in this class. Multiple processes running on a single processor, seemingly at the same time. In fact, indeed at the same time if you have multiple cores in your processor. Multiple threads, same idea, running within a single process, seemingly at the same time, or in fact sometimes in the same time. Because they can run completely in parallel, of course you have to worry about consistency, and you have to worry about locking your data and all the things you've been thinking about for all your assignments lately. And then signals and interrupt handlers are also technically concurrent. If you took CS 107E, you'll have known that you actually go and you handle interrupts from the system in a particular way. And what that means is, like, when you type a key on your keyboard, there is a signal generated to the operating system that says, a key just got pressed, deal with it. And then the operating system stops what it's doing, or has a process that's handling this that then does that. And so there's tons and tons of interrupts and signals that are being sent to your operating system while you're running your program. There are some programming languages that are specifically designed to use concurrency. Anybody ever programmed in the Erlang language? Phil has. It's a little tricky getting it to, like, it's getting your head wrapped around how it works is tricky, but it's specifically designed so that there can be no race conditions. Like, you can't really program it with race conditions. You have to think about that. And why would you want to do that? Lots of reasons, right? Once you understand how the programming part works, you don't have to worry about locking, you don't have to worry about race conditions and so forth. JavaScript is another example. JavaScript actually, and I was just talking to someone else about Python, is similar. They have the ability, well, JavaScript has one thread, and it just time slices all those, any different parts that are functions that are running so-called concurrently, just time slices them, and none of them actually run at the same time. Python does the same thing. There's this thing called the global interrupt lock, global interpreter lock, which means that you're running Python. You can say, I'm launching 20 threads in Python. Well, each one of them actually runs separately from the other, or independently and not at the same time as the others, because that's the way it works. But you don't have to worry about locks in that case. You just know that, I've got all these threads, they're going to just not have to worry about locking and so forth. Okay, so that's concurrency. By the end of this class, I think we've hammered concurrency pretty well. And then finally, the last principle that we've kind of discussed in this class is this client-server request and response, right? This is basically where you make a request to some entity and wait for the response to come back. Sometimes you wait, sometimes you have it fire a signal when it comes back and so forth. We first actually saw this with system calls. This was a request and response sort of thing. Remember, a system call is a function that the kernel owns and that you have no real control over. In fact, you don't even call it in the same way you call user functions, right? You actually, you have a call, or you basically send an interrupt to the operating system and say, hey, I've got something I'd like you to do, could you do it for me? And then you wait around until the operating system handles it, and that's request and response sort of system. Okay, HTTP, IMAP, DNS, all of these things are request and response, right? How are you doing this for your proxy server? Well, you get a request from the web browser into your proxy server, and then you turn that around and make a request to some other machine, which may also be a proxy server, which then makes a request to a website, etc. And then the response comes back, and you just wait for the responses. Now, you can make this look like you're not waiting around, right? Your web page, when you're loading some web page, it will come up in pieces, right? Because some of the responses are coming back one at a time, and it's kind of doing it. It does it as much as it can to make it seem like it's happening all at once. Okay, and then file systems are, again, request and response. If you want to get data from the file system, you need to actually request it, wait for the data to come back. Okay, all right. So that was the 7 different principles of system design. We talked about most of those in various contexts during the quarter. I've shown you a couple other new ones that we haven't really talked about in too much detail here. You can find those out in other classes and so forth. What questions do you have at this point? No other questions about this? Any other comments about this, Bill? No? Yes, Sam?
So is it completely impossible to multi-thread in Python?
Is it completely impossible to multi-thread? Okay, well, first of all, you are multi-threading. You can multi-thread in Python. But it's impossible for them to run at the same time on different cores, let's say. There's a lock that says any thread that's trying to use the interpreter has to wait. And why did they do that? That was an original design decision. It does limit the amount. It does make it so it's easier to write programs that are going to seem like they're that they're happening at exactly the same time. So mainly the reason for using threads in, let's say, Python is for your programs, to make your program easier to understand. Like you might say, I want to do 20 different things and I want them to all kind of progress at the same rate. Just do 20 different threads. Then you don't have to manage that yourself. The Python will manage it for you, basically. Yeah. Other questions? Yeah.
What kind of insight do you need to kind of design this like big systems where you don't actually know the details and everything?
Yeah. So what insight do you need to design big systems? Take some MS&E and take some like systems engineering classes. You can see the kind of the bigger picture there. I mean, look, understanding some of the details is good, but you have to be able to understand. You have to understand how the pieces fit together, really, right? And you have to make that interface very well defined, right? The people designing the copy machine, the person that's designing the part that like does the copy versus the person that's doing the like flipping over of the paper, they have to know how the interface between when that happens, right? That has to be very well defined. So I think knowing those parts of it are probably the most important, like being able to say, oh, okay, I might not understand how these two parts do it because I've got engineers doing those parts. I need to understand like how they interact with each other so that we get that part right. I think that's the big thing. But you know, a lot of times you have lots of meetings where you make you make plans on these things and you actually plan it out. I've talked to a few of you who have said, oh, you know, I actually sat down and wrote down my thoughts about how to do this program, and I actually think I did it faster, right? Well, good idea, right? And they do that for big projects. You want to have that planning phase before you even start to jump into any kind of coding or anything like that. Yeah, good question. What else? Okay, then we will see you last lab this Thursday, and then break, and then back after that.